So the topic here will be about how we achieve improvements in indoor air quality from an infection control perspective, but specifically how we can achieve this without inadvertently worsening other aspects of indoor air quality. Let's start with the basics in disease transmission that most of you would be aware of, but are worth briefly repeating. Viruses like SARS-CoV-2 cause a systemic infection, but replicate in significant amounts in the respiratory tract, where they can be expelled into the air around us. They are contained in respiratory droplets or aerosols that range in size from large enough to fall within a short distance due to the effects of gravity, to small enough to remain suspended for prolonged periods where they can be inhaled. The risk of infection ultimately comes down to how much viable virus is deposited in someone's respiratory tract in competition with their resistance to infection or immunity. The dose of viable virus someone receives and inhales is a function of exposure duration, the distance from the person emitting the particles, that is, the aerosols are more concentrated close to their source, exertion levels, for example, exercising with a high respiratory rate where you're increasing the amount of air your lungs process, rate of viral decontamination, which is a function of time, room temperature, relative humidity, and the presence of deactivating factors like UV light, and the rate of virus removal, which is either by deposition, ventilation, or filtration. The options, therefore, to reduce risk are to reduce the exposure duration, increase distance between people, mask to filter exhaled or inhaled air, ventilation, filtering the air, decontaminating the air, and promoting the uptake of vaccines. Looking at solutions that are sustainable long term, we are left mostly with the last few: ventilation, filtration of the air, and decontamination, as well as vaccines, with masks as something that can be implemented on demand. Let's look at some of these options. Natural ventilation. The simplest way to reduce risk indoors is to ventilate by opening windows and doors. Natural ventilation can be easily implemented where it's available, but several factors limit how effective and available it is. First of all, its effectiveness is dependent on several factors, including the presence of wind, the temperature gradient between the inside and the outside, as well as the size, location, and number of openings. Where outdoor air quality is poor, the use of natural ventilation can inadvertently decrease indoor air quality. Examples include proximity to sources of traffic pollution. To be honest, it's been a little disappointing seeing the number of new childcare facilities built immediately adjacent to major arterial roads, at least in our city. Days with high pollen counts, particularly on certain days where thunderstorm asthma is a risk, as well as bushfire smoke, an intermittent problem familiar to several regions around the world, including Australia and California. The availability of natural ventilation as a solution is also limited somewhat by the extremes in outdoor temperatures. Here's an example of one school in Australia over 2 days. It is in Melbourne, so hot one day, cold the next, showing the carbon dioxide readings throughout those 2 days. And what it demonstrates is that the ability to open the windows and hence maintain high levels of natural ventilation are very limited by the outside temperatures. You can see here for the first half of the day, the windows were open on both days, and in the second half of the day after lunch, the windows were necessarily closed. Natural ventilation can be a low energy intensive way to ventilate. That is until additional measures are required to then regulate the temperature inside. Where available, mechanical ventilation can be an effective way of introducing conditioned and filtered air exchanges into a space, but its installation needs to be matched with an assessment of efficacy and will require attention to ongoing maintenance. Here's a follow-up study of selection of schools in Victoria after the installation of mechanical ventilation systems, which incidentally are not common in Australia, that demonstrated elevated CO2 levels in many of these classrooms, suggesting that they're not meeting the recommended Australian standards of at least 10 to 12 litres per person per second of outside air. And the assumption of the presence of mechanical ventilation may actually provide a false sense of security that might lead to windows being kept closed where they might actually benefit from being opened. Other than mechanical ventilation or ventilation, virus can also be removed with filtration, whether it's installing filters in existing mechanical ventilation systems or installing portable air filters. So let's just briefly talk about filtration. Filters work by removing respiratory aerosols containing virus. How effective they are is dependent on how much air they process, at what level of filter efficiency, their proximity to the source of the aerosols, which in the case of infection control is usually inside and is one or many people, and the configuration of the device. That is, whether they are drawing air from the source of the aerosol or whether they are blowing air towards them. The way filters work is by removing large particles. You can see in this graph, uh, the size of the particles is on the bottom on the x-axis. So they remove large particles through either electrostatic or physical absorption. Those are particles on the right of the graph. So anything above 0.3 micrometers or so. While smaller particles, you can see that on the left of the graph, are removed predominantly through Brownian. Filter efficiency is usually measured at around 0.3 micrometers. While the virus is only 0.1 micrometers in size, you can see the red line there, the respiratory particles containing the virus tend to be larger in size, likely near to and above 1 micrometer, that is the green line and above, as has been suggested by some recent studies performed during this pandemic, specifically with SARS-CoV-2. HEPA filters capture at least 99.97% or greater of particles at that 0.3 micrometer, while filters used inductive ventilation that require lower resistance to airflow tend to have a lower efficiency to the smaller particles, but higher efficiency for larger particles that are still of interest to infection control. That is, particles the size of respiratory aerosols. As mentioned, where mechanical ventilation exists, filters and flow can often be upgraded to achieve air cleaning targets. Where this isn't possible, portable air filters can be used to achieve equivalent air cleaning targets that you would achieve with ventilation. These devices include devices with HEPA filters, like this device which has been deployed throughout Victorian schools, or self-assembled portable air cleaners using lower efficiency filters, such as these Causey-Rosenthal boxes that make up for their reduced single pass efficiency with higher flow rates. There is a potential to optimize solutions using portable air filters by ensuring the filter is in close proximity to the occupant emitting the infectious respiratory particles. If you know who this person is, it's easy. But in a room full of people, it may be that multiple medium-sized devices rather than one large device would increase the probability that it's located near them. Here is some computational flow dynamic modeling that demonstrates this, demonstrating the average concentration of particles in a room emitted from a source within the room falling quicker, that is the green line, where the portable filter is installed closer to them, versus when it's installed on the other side of the room. The primary challenge with portable air filters is sifting through manufacturers' claims on performance. What we're interested in for infection control is how quickly they clear particles of the relevant size from a space of a given volume, and at what noise level. There is little in terms of regulation or standardization for performance claims for these devices in Australia. Most devices marketed as air purifiers have been designed with pollution management in mind, not necessarily infection control. It might not seem like it's a significant issue at first, but it introduces significant implementation challenges, namely that most devices by default, when turned on, are in automatic mode running at their lowest fan speed until their onboard particle sensors detect particles, usually from cooking or bushfire smoke, at which point they then increase their fan speed. Respiratory particles aren't detected by these devices at the concentration at which they are found, so these sensors are irrelevant for infection control. In the US, air cleaners can be tested against a standard developed by the Association of Home Appliance Manufacturers, or AHAM, or in China, there is standard GBT 18801, they're both quite similar, involving placing a device inside a bedroom-sized 30 cubic meter chamber, filling it with particulate matter, and comparing the natural decay rate of this particulate matter with the decay rate once the device is turned on. This helps directly compare the performance of devices. This is very useful, but even then, manufacturers tend to report their clean air performance of their devices as their maximum speed. But noise levels on the lowest speed. Consumers then purchase these devices assuming an expected performance, but then they find they can't run them at the advertised clean air delivery rate and hence do not achieve the expected particle clearance rates. Noise levels are important. In environments like educational facilities where noise can disrupt learning and teaching, or healthcare facilities where noise can disrupt sleep, devices need to be selected to deliver clean air targets at appropriate levels. Information on noise levels for each of the fan speeds a device can run at is often actually difficult to find from the manufacturers, but are critical to allowing sustainable and effective use of devices. These noise levels need to be measured in a standardized way at the same distance from the device with the same background ambient noise level. Some manufacturers incorporate electronic cleaning technologies into their devices. These include bipolar ionization, photocatalytic oxidation, and ultraviolet light. First up, let's just talk about bipolar ionization. It's intended to reduce particle concentration in the room. It works by charging particles in a field, resulting in smaller particles agglomerating and precipitating out, either onto surfaces or onto charged plates. These can be used in ducted ventilation systems or in portable air cleaning devices. The potential unintended consequences of these include the production of ozone, secondary chemical transformations, including the production of volatile organic compounds, and have been found to actually increase the concentration of ultrafine particles under certain conditions. For example, through the secondary transformation of terpenes, these are compounds found in certain air fresheners. In addition, while they may meet ozone production limits on testing while the device is new, it may be because the power of the device has been reduced, meaning its efficacy is also less, or over time, through use, dust accumulating over charging plates can result in arcing, which can produce additional ozone. The impact of ionizers has been studied in college students in a dormitory environment, and there's one study suggesting elevated levels of systemic oxidative stress, either due to the negative ions themselves or secondary chemical transformations. Another technology is photocatalytic oxidation, or otherwise known as PCO. PCO involves shining UV light onto a catalyst, usually titanium dioxide, to produce hydroxyl radicals. They convert organic compounds into carbon dioxide and water, but under challenged conditions, using chemicals found in real-world settings, they've been shown to result in production of formaldehyde and acetaldehyde. You can see here in this photo, this is one portable air cleaner where they include both a HEPA filter and a PCO in the background. You've got a plate of titanium dioxide with a UV filter shining on it in the back. Ultraviolet light is a well-known technique to achieve microbial decontamination of surfaces and air. It is traditionally used in a configuration where a 254 nanometer wavelength light is shone into the upper zone of a space away from the occupants, and as the air is decontaminated as it circulates through the irradiation zone. The use of this requires sufficiently high ceilings and professional installation to ensure occupants are not put at risk of exposure above acceptable limits. Some portable air cleaning devices incorporate enclosed UV light, usually in addition to HEPA filtration. The benefit of having the UV enclosed is that there is no exposure to room occupants. It can often be difficult to tease apart the primary purpose of the UV in these devices, however, as some use it for photocatalytic oxidation and some for antimicrobial decontamination. You can see in this photo here the UV light at the bottom of the device. So to begin to understand the value that UV can add to portable air cleaning devices, we need to consider how UV works. To render microbes non-viable, it requires them to be exposed to UV at a high enough power or irradiance for a sufficiently long duration. This is clearly possible where they are floating near an exposed UV lamp in the upper zone of a room, but to achieve this in an enclosed device where the air is moving at very high velocity, achieving this is more difficult, requiring high-powered lamps to compensate for the short duration exposure. The higher the energy, the higher the potential secondary chemical transformations that become possible. In this case, the primary conversion of oxygen to ozone, a chemical with a variety of negative health impacts. As is the case with devices using other electronic cleaning technologies, manufacturers can reduce the power utilized to meet safety standards for production of ozone, but this then comes with a reduced efficacy. When it comes to including enclosed UV in devices with high efficiency air filter that removes 99.9% of particles, we have to ask ourselves, what value does it add? Here's an example from one manufacturer's own website showing the removal rate as a percentage of total due to HEPA filtration in the red, the total being green, and the UV in blue. You can see here that HEPA delivers 100% of the value in this particular device. Many devices, as mentioned, incorporate enclosed UV downstream of a good quality HEPA filter, where it is irradiating already filtered air. At most, it can add another 0.03% single pass clearance of the virus. And in the context of increased cost, energy utilization, and potential air chemistry concerns, the question is whether this inclusion is justified. There is an argument to be made that in certain high-risk environments like hospitals managing hardier microbes like fungi or multi-drug resistant bacteria that survive longer on filter surfaces than viruses, the inclusion of a UV lamp irradiating the capture surface of the filter may reduce risk at the time of filter maintenance. But by how much is not clear, and the device has to specifically be configured to deliver that UV to the capture surface of the filter. So in summary, to achieve effective improvements in indoor air quality in terms of infection control without inadvertently making other aspects of indoor air quality worse, we need to be clear in our goals. There are many options at our disposal. We need to understand that manufacturer claims may not always be aligned with these goals and have to put the effort into getting the right information. With time, it would be good to see these testing standards develop and regulation solidify around devices being sold in Australia and elsewhere. But until then, we have to do the best we can with what we have. Thank you very much for your time.